Welcome, guys, to another episode on my channel. And today we talk about neural nets. And the topic today is backpropagation. So, the question is, what is backpropagation? What is the basic idea behind backpropagation? Now, neural networks have this interesting capability that it's a network of a bunch of neurons, perceptrons, if you may like to call them, um, but essentially, it's a bunch of weights and biases, which are just essentially numbers. And as you get your inputs, it goes through each neuron, and each neuron just multiplies the incoming data with some weight, scales it, and then attaches a bias at every node. And then that goes through this activation threshold function, and then you basically get an output, and that's it. And this goes into another neuron, and so on and so on. And that's at the end, you get basically a network of these neurons working together to produce an output. So, what is this big idea behind backpropagation? Backpropagation is an idea that in order to train this network, in our case, we have taken the world's simplest neural net, which is just a single neuron. Now, it's easier to see whatever ideas we're going to talk about. It's much easier to see the ideas in isolation when you look at just a single neuron. What we're going to do is the error function for this is defined as whatever is the target for when we compute this output. We also have a target, which is what we expect the output to be. So the error function is defined as target minus the output whole squared over 2. We'll work with that. And you'll see that this is a very nice error function because it turns out that when you differentiate, when you take a partial derivative of this function with respect to the out one, it turns out to be this out one minus target one, which is very nice. Um, so what we really want to do is that we want to take this partial derivative with respect to this weight or with respect to the bias for that matter. Why do we want to do that? We want to do that because if you consider optimizing an error function, which is in our case very nicely shaped. It's nicely shaped because it has this global minima. It's like looks like a well, right? And you can add any number of variables, but because all the variables are defined in this format that this is target minus output whole squared over 2, there could be multiple neurons, but you'll always sum them up in this fashion. You'll realize that this will um, form this nice inverted bell-shaped curve. Now, when you differentiate this inverted bell-shaped curve with respect to any of these weights, let's say W1, in our case, we only have one weight. So if you differentiate and the slope is negative, what does this mean? You're left side of this global minima. So you have to nudge it in the forward direction. But if the slope is positive, you have to come back. So you have to subtract something. So that's why we get this minus sign. So minus del E over del W gives us the change um, that we need to, that the slope is telling us the change. Either we have to go left or we have to go right. It's telling us this minus del E over del W gives us how to approach towards the global minima. Now, we also have this alphabet eta here, the Greek alphabet, which is telling us the learning rate. And we have to nudge this change so that we don't go very fast or very slow. We just choose the right appropriate amount of change here that needs to be applied to our initial guess, or at some point you have some guess, and it's slowly converging so that the correction is this thing. So that's why I guess we need our partial derivatives. Now I'm going to go back to this equation here, that this del E or del W is what we needed in that equation to compute the nudge factor for this weight. Now, this del E over del W can be written as del E over del out 1, which is the output of the activation function, and times, using the chain rule, del out over del net 1 times del net 1 over del W1. So you can do partial derivative with respect to this, then with respect to this, and eventually getting back to this. What does that turn out to be? There are three expressions in this. Let's do the first one. Del E over del out 1, this is just our error function, right? This error quality function. So that when you differentiate this, you get 2 cancels out, target minus out 1, and the partial differential of this, which is minus 1. So you get all this here. The second one is out 1 over net 1. Out 1 over net 1 is just the differential of this sigmoid function in our case, and this turns out to be out 1 times 1 minus out 1, and then net 1 over W1 is nothing but H1. So partial derivative is H1. Now this is with respect to this weight 1. Now what is the derivative with respect to the bias 1? It's even simpler, because this net 1 over del b1 is nothing but a 1, because there is no other weight here. Bias is just going straight. The weight is always 1 here. So that becomes a 1. So you just drop this factor when you want to do differential with respect to the bias. There is no h1 here. You just take this part. And that's about it for this idea. So now the question is, now you know how to differentiate, get this partial derivative. You know how to plug them, how to plug the learning rate, and how to nudge this weight or bias for that matter um, in any state where you are trying to run. Now, what is this whole idea about? How do we apply this to the fact that we have a large data set which we are trying to train on? How does it help us? Where does it all fit? The way it fits is that you compute this error, because in the beginning we will just guess, right? So let's just move to that. We will guess our W1 and B1. So let's say we guess our W1 to be 1, B1 to be 0. And then we plug that, we run through all our data set, and we compute the outputs, and compare them to expected outputs, and compare and come up with the partial derivatives and so on. And then using them for every data sample in our data set, we're going to compute this partial derivative and the nudge required for any weight or a bias, any weight or bias. And then once you have run through all of these, then you can average these nudges. And for any given, let's say for W1, we can compute what the nudge is over all these samples of the data set, and we can average them. Once you do that averaging, you would get what the nudge really should be, and then you can apply the nudge at the end of this pass. This whole pass is called an epoch, right? So in our case, I've shown you that you can compute the partial derivative here using this formula here, and it turns out to be minus 0.04, right? So these are just numbers. They're already there. They're part of this calculation, right? When you run your neural net, just simply forward neural net, which is just y equals w1 h1 plus b1, and then the sigmoid function. Just the act of doing that produces everything that you need for this backpropagation rule. All these variables are available to you. You can just plug them in and you get the partial derivative. It's nothing fancy. It's just a simple math here. Just multiply, subtract, multiply, and that's it. There is no differential calculus involved here. If you're trying to do this in an FPGA or doing this embedded system, it's easy, right? Because all you have to do is this right side, which is just some simple math. If you do this math and then at the end of this run through all the data set and do an average, you have then the mechanism to nudge all your weights and biases in the right direction. And now that you can do that, now let's dive into our Python code and see how we can do that. So for that, I have prepared this Python file, and this Python file is essentially, if I just zoom in here so you can see it better, um, this Python file is actually not showing correctly on your screen yet. So I'm going to scale this correctly. So if you do that, you can see now that this Python file is showing this neural net model. What is this model? So in this case, we have math because we need some of these math functions like e power minus x, etc. Matplotlib because we want to plot the error function as we do the epochs. Now our input and output was shown earlier. It's very simple. We're basically trying to compute 1 minus x, right? And if you input 0.9, you get 0.1. If you input 0.8, you get 0.2, and so on. Very simple data set. Now the forward pass is our model. Because it's only a single neuron, it's pretty straightforward. The net will be x times w plus b. Output will be a sigmoid, and that's it. And you return the out and the net, right? Now what is this backpropagation algorithm? Backpropagation algorithm takes two parameters, the learning rate and the number of epochs. What it's going to do is that it's going to take all these inputs and outputs, and it's going to run over the epochs. And what is an epoch? When you go over every data set, every sample in your data set, it's an epoch. And you would basically start with some random weights and biases. In our case, weight was 1, bias was 0. And we're going to run through the epoch and figure out what the nudge factor would be for every weight and bias. In our case, there's only one weight and bias. So once again, it's very simple. And simple is good because we can understand the mechanics of how this all works. If you look at something with a bunch of nodes, then you'll get probably a little confused on what all's happening and why is it happening and so on. But in this case, very easy to see what's going on. So we run through the epochs, and then inside the epoch loop, we have this every input, right? So at every epoch, we're going to run through all the samples in our data set. And for each one, we're going to compute the net, the neural net, which is the forward pass. When you run through the forward pass, you get the values for the intermediate nodes in the network. Now, remember, a network looks like this. So you need the value for net 1, H1 and W1, B1 are known because those are inputs. Then you get net 1 and out 1. So that's what this thing actually gave us. That in this pass, this forward pass gives us this res, and res has two values, out and net, right? It gives you those. So, and then you compute the error. What is the error function? Error function is simply the res, which is the out, minus the expected output whole squared over 2, and we compute that error. So once you've done this error over every sample in the data set, for that epoch, the epoch's forward pass is complete. And in this, you can print out what the total, what the epoch number is, what the error is, what the weights are, what the biases are, etc. So we'll see that when we run this function. And we can uh, add the error to our error plot so we can see an error plot at the end of all the epochs. You can see what was happening to the error as the epochs proceeded. Now, how do we do our partial derivatives? So remember, the partial derivative equation was very nice and it looked like this. And just so you appreciate it, these are all variables that we know already. Once we do our forward pass, we know these variables because these are just, you know, the outputs that are computed minus the expected outputs which were given to us in the beginning, and this new out times 1 minus new out. These are all calculated in our forward pass, and the input was given to us. So there you go. We have our partial derivative with respect to the weights, partial derivative with respect to the bias. We have these values. Now we store all of them for every data sample that we compute. We store all of them into this array. And at the end, we just take an average. So we take the average over partial derivatives of W, and we get the new partial derivative of W. We get the partial derivatives average over B, or the bias, and you get the new partial derivatives for the bias. How much do you nudge now? So you nudge by the learning rate and with a negative sign. We saw that why the negative sign was there, because when your partial derivative is negative, you have to go forward. When the partial derivative is positive, you have to go backwards. So because of that, to reach this global minima, you have to apply that rule. So we see that here, that the bias has to be shifted by minus learning rate times partial derivative with respect to the bias, and the weight have to be shifted by learning rate times partial derivative with respect to the W. So if you do that, one pass is now complete. And if the pass is complete, it's going to repeat it with the next epoch. And as you repeat this whole epoch, you're going to change your weights and biases so that eventually you converge. Why are you converging? Why are you converging? Because of this. The magic is right here, right? You're not comparing it to anything, but we're just trying to make sure that the partial derivative is moving in a direction. It's moving in a direction so that we are going towards this minimum. It's not really visible here. If you look at this code, you're like, where is it trying to take you to the minimum? It's trying to take you to the minimum by this equation. This is the magic. This equation is the magic because whatever is the partial derivative, it moves you in the reverse direction of the partial derivative so that you reach the bottom of this well. And that is the magic right here in these. And that's why when you compute at the end of the epoch, your movement is taking automatically to the minimum of the well. And so you just keep running this over and over and over till you converge or go down to a very, very small change in your error function. And so then we plot this and we show this. So now Let's just see if we can run this. So I'm going to again zoom out and scale this so that you can see my screen better. And all I have to do now is I have to just run this um, backpropagation Python. And you can see that it is running to almost, it's running to 5,000 iterations. And at the end of 5,000 iterations, the error function is very, very small, right? If you just go back up, you can see the error function, used to be larger. If you go at the top, it was like, it's an order of magnitude more. This was 0.45 in the beginning and it ended up 0.016, right? So now let's look at the how the error function changed over time. At the 5,000, that's 0.016, but at the beginning it was like 0.44. So from 0.44, the error function fell down sharply and then it collapsed slowly, slowly till it very, very slow here, right? Change is very, very slow here. You see that it's like, the fourth decimal place is what is even that is not changing. It's like fifth decimal place is changing now. So it's very, very small changes. And so you have converged, and the backpropagation algorithm has succeeded in bringing you in this training exercise down to a stable point. And you're very, very close to this bottom point here. That's why the training is converging and the number of epochs is just about right. Now, if you keep increasing the epochs, it's just going to take more and more time, but your results not going to vary that much. So it's a good trained neural net. You can take these final weights and biases here, minus 3.219, and the bias being 1.464. You can take those weights and biases, plug them into your machine, and start decoding. And that should give you pretty good results, very close to what you expected. So that's it for this episode, guys. Thanks very much for watching. If you liked and enjoyed, and if this episode helped clarify anything for you, hit like and subscribe on my channel. And if not, then leave me some comments and I will look at them and respond accordingly. I will continue to bring another episode in this just to show you how this idea can be extended to multiple neurons. It's very complicated when we start by looking at multiple neurons and try to apply this differential calculus. It seems daunting, but if you apply some simplicity and apply some tricks so that you can simplify them, then you'll see that this is manageable, and you could even write a Python function to compute the this calculus inside your program. Now, what is the advantage of that idea is that you can then apply them to hardware, FPGAs, embedded programs, and so on. So that's the advantage. Is don't just think that it's done by TensorFlow and Keras and it cannot be done by you. It's very complicated. No, it is simple. It can be applied. It can be understood and applied in simple math form. So that is the key to this episode. Is if there's one takeaway, which is going to be that you should feel that you can do this on your own. You don't need TensorFlow and Keras to do this for you. So thanks a lot for watching this episode, guys, and I'll see you in another episode. Until then, take care and bye bye.